Okay, hello, my name is Nikola Varichuk. My student number is 101432361. This is my assignment 2 for Comp3132. Alright, so first of all, since we can't import our dataset from Keras, we manually upload the iris assignment2.csv, and we name it file name. We then displayed the first 5 rows of our dataset to check if it loaded properly. The species column originally contains text values or strings, Setosa, versicolor, and Virginia. Here we can only see Setosa though. Since machine learning models work better with numerical values, we map them as follows. Setosa 0, versicolor 1, and Virginica 2. Using .map, of course. Okay. And then we checked if they were applied to the species, and it was. So for number 3, we're splitting our features, X, and labels, Y. So we split our data set into 2 parts, the features and the target labels, X and Y. This separates the input features from the output labels. This is X, and we print X, and then we print the output labels right here. For number 4, we split the data into training and testing sets. So X train, X test, Y train, Y test, with a test size of 0.2 and a random state of 123. Setting random state to 123 ensures reproducibility, so we get the same results. This is an 80-20 split, of course. We then print if the data has been split successfully. It has. And then we just print the first 5 rows of the train and test sets of each. Right here. We then check the length. We print the length, and we ideally wanted it to be 120 and 30, and we checked if X train and X test are equal to that. I added a conditional statement just to make it more visually appealing, I guess, to verify that the data is split correctly. We then did one-hot encoding for Y train and Y test. Since we're working with a classification problem, we converted our labels into one-hot encoding using TensorFlow's toCategorical function right here. This transformation allows the neural network to output probabilities for each class. So for 6, we then build the neural network. We built a neural network using the TensorFlow sequential API. The model consists of 2 hidden layers with 100 neurons each. Using the ReLU activation function, an output layer with 3 neurons using softmax, since we're predicting one of 3 classes. Okay, so for 7, we compiled and trained the model, but before training we compiled it. Using the RMS prop optimizer and the loss function categorical cross entropy. with an accuracy metric. We then trained it using 20 epochs and a batch size of 10, right here. Once the training was complete, we evaluated it in the test set to see how well it generated. This gave us a final accuracy score, which tells us how our model performed on unseen data, which is pretty good. And then we repeated everything in 9 by experimenting with smaller models to see kind of how parameters affect our performance, or hyperparameters really. And then we created a smaller version with fewer neurons and compiled it with the same optimizer and loss function. Then we trained it for 4 epochs instead of 20. Finally, we evaluated this smaller model to compare performance. Okay, so for number 10, first question is, how do the number of layers or hidden units impact the accuracy of our model? Well, more layers and neurons allow the model to capture complex patterns, which can improve accuracy, but too many can lead to overfitting, where the model remembers the training data and doesn't generalize it that well. Do we always suffer from overfitting? One way, by comparing no, but it is common in deep learning. If a model is too complex for the data set, it will perform well on training data, but poorly on new data. But with proper tuning, we can prevent it. Number 3 is, how can we detect overfitting? A way to detect overfitting is by comparing training and testing accuracy. If the training accuracy is high but the test accuracy is lower, then the model is overfitting. We can also plot loss curves. If validation loss increases while training loss decreases, that's a sign of overfitting. For question 4, how can we reduce overfitting? There's more than a few ways to reduce overfitting, but you can reduce model complexity, meaning reducing the neurons and adding fewer layers. There's early stopping, where you stop training when validation accuracy stops improving. Dropout layers, randomly ignore some neurons to force the model to generalize. So I think that concludes my assignment 2. Thank you for listening, and have a good day.